Next speaker is Olivier Catoni. He will speak about generation free fast bias bubble for gravimetrics. Please.
I would like to thank the organizers for their kind invitation. It's a pleasure to speak here. And I'm going to talk about the estimation of the gravimetrics. And the results I will present are obtained using the fact bias methodology. So I consider IID vector valued random variable xi, and I would like to estimate the quadratic form that is related to the ground matrix, that is the expectation of the scalar product between x and theta of x squared in each direction theta. So of course this is some way to estimate the expected ground matrix, that is the expectation of x transpose under the distribution of the marginal distribution of xi. And the assumption I will make is that the trace of G, that is also the expectation of the norm to the square of x is finite. I will not use the usual empirical ground matrix that is obtained by replacing the distribution here by the empirical distribution of the observation. I will introduce a robust estimator using an influence function psi, and I will choose this special type of influence function. So this is a function that is symmetric, that is bounded by log 2, and that is between minus, it is bounded from below by minus log of 1 minus c plus z squared over 2, and from above by this thing. So the exponential of psi is bounded, it's between two polynomials of power 2 in z. And this is what is important to. So the exponential moment of psi of z, when z is a random variable, is related to the first and second order moments of z. So, of course, I will consider the observable distribution, that is the empirical distribution of the sample, and I will be interested in an empirical quantity that is centered and that is sub-thresholded by applying the influence function psi. So psi is an approximation of the identity on the neighborhood of 0. So when lambda is small, this is almost as if we had the identity instead of psi, and in this case, this is going to at least an expectation to give what we want to estimate. We want to estimate this quadratic form here, and so this makes sense to choose for the estimate of theta and hat of theta. So you may think that theta is of norm 1, for instance, and so you consider alpha theta, where alpha is the norm of alpha theta, and you take the value of alpha for which this is going to be 0. So R lambda of alpha theta is increasing in alpha because you have alpha square here, and it starts when alpha is equal to 0. This is negative, and so in cases when this is becoming positive for large values of alpha, you will have 0 here, and in other case you will estimate the norm by 0. Okay, so in good cases we have R lambda of alpha theta equal to 0. That is, we have centered the application of the soft thresholding here. And so what can we prove for this estimator, where we have thresholded by an influence function the usual empirical estimator of the expectation?
Olivier, why is it 1 over alpha? I would have guessed that it was 1 over square root alpha. Why is it n hat of theta?
This is what gives you this. If you
Yeah, I see. So if you have alpha theta in n, then you get an alpha squared outside.
Yeah,
But-
you get alpha square and n theta minus 1 equals 0, so n theta equals 1 over alpha square.
I agree. Oh yeah, okay. Ah, okay. Understood. Yeah.
Alpha squared times n theta equal 1, essentially.
Yes.
Close to 1, so n theta close to 1 over alpha squared. So the benefit of using an influence function is that I'm getting, so this result is a dimension dependent result. Sorry, RD is the dimension of the ambient space. And so the assumption I've got, the result is based on an assumption on this kurtosis coefficient kappa. That is the only assumption I need about the tail distributions of the random variable I'm interested in here is theta times x to the square, and so I'm controlling the ratio between the moment of order 4 and the square of the moment of order 2 of what I'm trying to estimate. I'm trying to estimate this expectation, so I need some hypotheses on the variance and on the tail distribution. And it turns out that if I got an hypothesis on the variance using the influence function psi, I don't need any further information about the tail distribution. So for instance, if I'm in the Gaussian case, in the Gaussian case, kappa is equal to 3. In non-Gaussian cases, kappa can be larger, but if it stays relatively, if it takes reasonable values, and we know about, so you can take kappa here, but if you don't know kappa, you can take an upper bound for kappa that you know, and then you've got a scale parameter to choose here. It is a scale parameter in the influence function, so I need to know the scale parameter here. And I can take this scale parameter as a function of my hypothesis and the moment of order 4. And so basically lambda is equal to d over n, the square root of d over n. And then for any epsilon, so epsilon is the confidence level of what I'm going to get. I'm going to get a result with probability 1 minus 2 epsilon. I choose my my scale coefficient in this way. And for values of n that are larger, essentially to d kappa d, so a log of epsilon minus 1, I have an uniform control of the ratio between the true energy, expected energy in direction theta and my estimate of this quadratic form. So the ratio is close to 1, and the distance from 1 is of order d square root of d over n.
So,
Yes.
can you explain, you do it via an influence function, what if I just did it the standard way?
And if you do it the standard way, you need heavier assumptions on the tail distribution than this fourth moment assumption here. I can do the fourth moment assumption only here because when I take the line of proof is Packby's theorem based on the Chernoff bound for a fixed value of theta, and the Chernoff bound for psi here will involve the expectation of the exponential of psi, and the expectation of the exponential of psi is bounded by the fourth moment. Here I've got theta times x to the square, so I will need some hypothesis about the expectation of theta times x to the power 4. And this is, and if I want this weak hypothesis on the tail distribution, I need the influence function. But if I'm ready to assume exponential moments, bounds, I could run the Packby's methodology without without using the influence multiplier. So, for instance, for Gaussian, in the Gaussian case, although I didn't write it down, I'm pretty sure I can write down everything for the empirical grand matrix, taking as an estimator of the empirical grand matrix. So the speed here is quite, so we have two terms here, both are order d over n. So this term is quite satisfactory because you have 2 times the variance term, and it is exactly the variance term, because when you assume this, the variance is going to be, the variance of n theta is going to be bounded by kappa minus 1 n theta squared under this assumption. So as you divide by n theta, you get 2 times the variance times a complexity measure over n. And here the complexity measure is the minus the log of the level you want, the confidence level, plus a measure of complexity that is essentially the dimension. So this is satisfactory. Here you have a second term of order kappa d over n, and of course this 89 is a little less satisfactory, but I think the reason why there is this numerical constant is in the technicality of the proofs. And one nice thing is that to choose the scale parameter lambda, you don't have this Pegler constant here.
So here your theta is fixed. Could you claim something uniform in theta?
Right, it's uniform in theta.
No, it's uniform.
It is.
The point, all the point is that it's with probability 1 minus 2 epsilons for any theta. It's uniform
Okay,
in theta.
so this
Yes.
is super.
Yeah. If there were no uniformity in theta, this would not be interesting. So the point is that you have estimated the ellipsoid of inertia uniformly. Sorry.
Can I ask a question? So if you were to write that as the probability that the ratio -1 absolute value exceeds t, you would have an exponential bound, right?
Sorry.
So let's say you write this, instead of like solving this thing as statistical, but let's say I want to find an exponential bound of the probability of deviation from 1, okay, of the ratio.
Yeah.
Let's say I put epsilon is equal to, or t is equal to mu over 1 minus 2.
You've got
Do I
exponential
get this
constant.
thing? Do I get to get t as close as I? Do I get my confidence level to go as close as I want to 1 or not?
The limitation is that n will be, so if epsilon goes to 0, the condition of n goes to infinity here. But this is the ordinary limitation.
Okay, so you have some conditional, and I mean, it's the
Yeah,
same
because
thing as in the
because you have
paper
you have
with-
1 minus 2 mu here. So the bound is exploding for mu equal 1 over 2. Mu is this. So this explains that you have a condition of an n, that is essentially that of that magnitude.
Okay.
Okay. So I can go to any value of epsilon if n is when n is growing. But I mean the requirement is quite weak. The requirement is that n is of order log of epsilon. You can go to exponential minus n something, which is really low as a confidence level.
Yeah.
So essentially, you can go to confidence level. Epsilon can be very close to 0 because the requirement is in exponential minus n. Does it answer your question?
Yeah, it does.
And the dependence on t, is it somehow optimal? It seems it's Gaussian, it should be log d.
No,
The dependence on the dimension.
yeah, the dimension d is d over n is the speed of convergence in least square estimation, and so it's the optimal.
No, because it's here you're interested in the probability bound.
Sorry.
Because you are interested in the probability bound.
But still,
D parameter. Take just a random matrix with identity covariance. One eigenvalue is 1 plus square root of the D over n squared.
Yeah, and you can't go faster uniformly than d over n. And you get some. Sorry?
Then you get some fast form.
I'm going to give a dimension-independent bound later in the talk. Well, we replace this D by something that is independent from D. Okay. So wait a minute. So I'm taking time. So one problem here is that I'm estimating a quadratic form n, but my estimator n hat is not necessarily quadratic because I used this centering process here, so I'm not sure I get a quadratic for n hat. But generally, once you have a confidence interval for n hat, this is what I get. I get for uniformly inferior confidence interval for n hat. Then I know that there is with probability 1 minus 2 epsilons, I know that there is indeed a quadratic form satisfying these constraints, and I can compute it by using an algorithm that is the algorithm used for support vector machines. I can compute a g hat that is expressed as if I take a finite set of values of theta, for instance, I have a delta net on the sphere, then I can work out a g hat that I represent as the sum of the theta of psi of theta times theta transpose, where psi is the minimization of a quadratic, of a convex problem. And if I decompose psi into psi plus minus psi minus, where psi plus and psi minus are the positive and negative parts of psi, I have to solve a quadratic problem in the positive order. So this is we have fast algorithm to do that, and G hat will minimize the Frobenius norm within the matrix. G hat is the solution of these constraints. The matrix, the quadratic form satisfying these constraints, minimizing the Frobenius norm. So the Frobenius norm of G hat will be less than the Frobenius norm of G, but it's less than the trace of G to the square. So I can control also the gradient of G hat of the quadratic form associated to G hat. So the fluctuations between theta 2 and theta 1 are controlled by the trace of G, and I assume that this was finite. So by taking delta, by having delta goes to being sufficiently small, I can get this. I can ensure that G hat of theta transpose theta is within the same confidence interval up to some error that can be made arbitrarily. So essentially, I can get a true quadratic form within almost the same confidence interval. And so the proof is that I choose G hat to minimize the Frobenius norm here, and this is the usual duality formulation, and the static condition is satisfied, so there is no duality gap, and I can reverse the order of minimization, and I obtain this representation for G hat. So now, when I have this kind of estimate, something I discovered quite recently, and maybe when I have a uniform estimate on the quadratic norm associated with the Gram matrix, I can solve these square regression problems in the following way. So now I'm considering a least square problem. So I've got two random vector, a random vector x and a random real variable y. I've got independent copies, and I'm interested in the usual least square problem. I want to find theta that minimizes the risk, that is the expectation of theta x minus theta scalar x minus y to the square. As I've got estimation of quadratic form, I will consider the homogeneous problem. So this is not homogeneous, but I can add a gamma to get an homogeneous quadratic form here, and theta and gamma. So I want to solve the minimum of in theta of n of theta 1. So this is of the form I studied. This is a scalar product in dimension d plus 1. And if I have a bound for n, if I have a quadratic estimator n hat with a bound of this form, and this is the kind of bound I showed previously, then I can prove that the optimal value of the parameter feeder star that minimizes R is linked, so with the same confidence level, with my estimator feeder hat. So feeder hat will be the odd mean of n hat of feeder 1, because n hat of feeder 1 is the estimator for R feeder. And I got this very simple chain of inequality. The excess risk of feeder hat is bounded by a feeder square, so the square here is important, times n hat of feeder hat 1, and as feeder hat is minimizing this, which is less than this, and as we have this relation, this is less than this. So if you read this inequality, you've got the speed of convergence of the estimator. The excess risk is bounded by, so when either is of order square root of d over n, either square is of order d over n, and this is why you can't get better than d over n uniformly, because elsewhere you could solve quadratic regression faster than d over n, and if you make a computation for Gaussian, the Gaussian case, even in fixed design, it's d over n, don't go faster than that. And so this is quite, and here you've got something that would be the noise variance if we had made hypotheses about the fact that y was feeder star x plus noise. So here you've got the noise variance. So this is quite satisfactory. And moreover, you have an observable confidence region, because you can. So this is equal to this. This is well known. And I've got an estimate, uniform estimate for this one. So I know that feeder star is in the confidence region defined by this inequality here. So essentially, when you have a uniform bound of this kind on the ground matrix, you can estimate the whole geometry of this square regression in a satisfactory way. So this derivation here is really one simple chain of inequalities based on the polarization formula. Here you, maybe I don't have time to do it in detail, but you just make the remark that when you have a quadratic form and when a parabola is symmetric with respect to its minimum, so this is going, whatever value of feeder prime here, this is going to be equal to 0. So this is lower bounded by this, according to my bound. So here, using polarization, I get only the cross product here, that is feeder height. And I can, and of course, now I can use that the gradient is 0 at feeder star. So I'm controlling this thing, and well, I don't have time to go into the details. This is really a one-line, one chain of simple inequalities based on the control of the gradient, in fact. Because here I'm controlling the gradient by taking the supremum feeder prime, and this is how the square root appears. Okay. So now let me give you a dimension-free bound. So the setting is the same as before, but the bound is different. I'm going to bound the ratio between n hat and n. Previously it was the ratio between n and n hat, but this makes no difference. But now the bound here will be of the same kind as before. It was 2 times kappa minus 1, now it's 2.07. It was, and here I've got, yes, I put n less than 10 to the power 20, because here you've got a log n. So if I can go to 10 to the power 40 if you want, or 10 to the power 100, and I claim that you will seldom encounter sample sizes larger than 10 to the power 20. So one message is that log n is a constant. Really, but you have log of 1 plus log n of log 20. So it's less than 4.3. Okay, and then the dimension is replaced. Say, for instance, in the case when you normalize feeder to be of norm 1, here you will have the ratio between the trace of G and the energy in the direction theta. So this is what is replacing the dimension. And of course, if in the case when you choose a representation in which G is equal to identity, if G is equal to identity, you recover D here. Okay, so that's it. Yeah, D, which is what you get when G is the identity, is replaced by the amount of energy in direction theta compared to the total energy of the clouded points. Okay, and the constants are a little worse, but not too much. And of course, the trace of G is the total energy. And in any orthogonal basis, we've got that it is equal to this because the trace is invariant when we change the basis. Okay. So now I can give a glimpse of the proof. I will not prove this, but I will make some comments on the ingredient of the proof of this theorem. So here n hat is something more complicated than in the last slide, because I have to tune adaptively the value of the scale parameter lambda. So I have to work with the grid of values of lambda and have an estimator that somehow choose the optimal value of lambda.
It could be worse, trace of D divided by n theta.
Sorry?
It could be bigger than D.
Yes, but in case you choose a representation, because you can the scalar product between theta and x is invariant if you make if you replace theta by n by say u times theta and x by u minus 1 times x, right? And if you work and if you take a representation in which g is if you replace x by g to the minus 1/2 x and theta by g to the g to the power 1/2 theta, then in this new set of coordinates, g is going to be the identity, and you will get d here. But of course, you can have larger and lower values here. And this is what is interesting, is that you don't depend on the dimension. So this generalizes to a Hilbert space. You can have a trade distribution of eigenvalues here. You are independent of D. For instance, if you have only a few large eigenvalues and then very small eigenvalues, the tail distribution of the eigenvalues that is small, then here you will have for the first eigenvectors or for the vector space generated by the first eigenvector, you will have something that is not depending on D, larger than D, and of course, for the smallest eigenvectors, you will have something larger than D, because this is something to trace of G, and in particular when you take eigenvectors here. Okay, so to the proof, you use the same influence function, and it's a perturbative proof. That is, we consider Gaussian perturbations of the parameter theta. So we have a parameter theta that is the strength of the perturbation of theta. And I consider also SAM, I'm working with theta such that the norm of theta is equal to 1, and I'm considering the alpha hat that is going to center this representation here. So the first thing is to relate. So I want a result that is uniform in theta, and I'm going to relate the value of what I'm trying to estimate the expectation of psi of theta x to the square minus lambda. And so first thing to do is to relate this to a quantity that is randomized with respect to a Gaussian measure centered in theta. So I can compare this to this by doing some, it's elementary, but I will not go into the details. So here, the important thing is that theta is not present anymore, except that I have a random, I'm taking the integral with respect to the distribution of p theta, but it is an expectation with respect to theta prime. And here I've got essentially so log of 1 plus something is almost equal to something. So this is almost, and this is also almost the identity. So I've got the main term here, and I've got some spurious terms due to the fact that I'm using a perturbation. So this is the first thing to do. And this is obtained by remarking that the second derivative of psi is larger than -2, and we do some elementary computations that I will not detail. And the second ingredient is a packed-bias lemma. If you consider a function of x and theta, you can compare the empirical mean of the randomized value of log of 1 plus f of x and theta uniformly under any perturbation. So the important thing is that it's working with 41 minus epsilon for any values of the perturbation rho. This is going to be less than the expectation of the randomized f of x and theta plus a term where the complexity is bounded by the relative entropy of rho, but can be random here, because it's up to 1 minus epsilon, with respect to a fixed measure on the parameter space, mu. And the proof is based on this simple inequality that is related to the fact that the Legendre transform of the log Laplace is the relative entropy. So if you combine this thing with this one, then you obtain this sort of inequality here, where I relate my empirical the empirical mean with an expectation. And here, as I've chosen, I choose for my reference measure the Gaussian centered in 0. So the complexity term that is emerging is the square of the norm of theta over 2n. Right? So this explains why this is where comes this is the way I can have either a dimension bound here or something related to the trace of G and the distribution of energies in the direction. Okay, so when I got that, I use Cauchy-Schwarz to have simple things here, separating the expectation with respect to x, and this is how I need to introduce kappa. And so I get upper and lower bounds for my empirical quantities then here, and then doing some massaging with these equations, you can get a lower bound and an upper bound for n theta. And once you have these lower and upper bounds, you have a lower bound and an upper bound that depends on two parameters: the scale parameter used with the influence function, and beta that measures the strength of the perturbation. So once I've got all these bounds, I make things uniform in lambda and beta by using a grid and the usual union bound. When I've got these, I optimize in lambda and beta the lower bound and the upper bound. I take a sup and to get bounds b minus and b plus that are still observable but independent of lambda and beta. And I take as my estimator n hat the middle of my confidence interval. So I pick a confidence interval and then I take the middle, and I think my time is finished. So this is essentially the main ingredients of the proof, and I will click on that side. And yeah, and thank you for your attention.
Short question.
So, I mean, it's really impressive that you get completely dimension free. Like you don't have any log d. There is nothing.
So you can apply it using the representation in a reproducing kernel Hilbert space, for instance, where the dimension is infinite. This opens the possibility to apply the bound in a representation in an infinite dimensional Hilbert space with using a reproducible kernel.
Very short.
Okay, so at some point when you, I don't know if it's going to be very short, when you went back to your to the bound on the regression, you still have R of theta star as a factor of your bound, right? So if R of theta star is actually large, then you don't get. So remember when you went from this result and had to run -1 is bounded, and you went to the oracle inequality, you have R of theta star on the right hand side. What would it take to get rid of this?
You can't get rid of this. Is essentially the variance of the noise.
Yeah, if you're well specified, but if you're not, I just want the variance of the noise. Let's say I don't want it essentially, I want it.
Yeah, but this is the variance of the noise. You can't get lower than the variance of the noise, I think, in this setting.
This is the variance of the noise plus the systematic value. If y is not equal
Yes,
to
but you don't, okay, but I don't know. Wait, yes, but
I mean, maybe it's here, I don't know.
I don't see how, because you don't make any hypothesis, so nothing. You don't make.
Yeah, but in aggregation, when you use a normal inequality for
You
aggregation, you
stay
get
in
a
your
uniform
model.
value.
I'm comparing to the best possible thing in the model. Well, maybe I don't know. Maybe you can go if you specify. But in full generality, if you don't make further assumption, clearly I don't see how you can go lower than this, which at least in the least probable case, it will be the variance of the noise.
The most okay, but I want
Almost
to
all
get
this,
hit
but in some cases included in the hypothesis here, you will get the variance of the noise.
Thank you. This is a very satisfactory answer.
No, but I am not, and maybe you can go further, but I